Today, let's open up the chemist's toolkit. We're going to look at a few brilliant ideas that let us measure and work with a world that's completely invisible. I mean, how do you even begin to mess with the building blocks of matter itself?
It's a huge question, right? Everything, literally everything, is made of atoms. But they are so unbelievably small and there are so many of them, you can't just pick one up and put it on a scale. So chemists had to figure out a way around that.
And you see the result of their solution every day. This medicine label is a perfect example. That concentration, 5 milligrams per milliliter, isn't just a suggestion. Getting it exactly right can be a matter of life and death. And to get that level of precision, it all starts with figuring out how to measure the invisible. And that really is the core of it all. We can't see them, and we definitely can't count them one by one. Trying to do that would be like trying to count every single grain of sand on every beach in the entire world. It's just not possible. So they needed a really clever workaround.
So that brings us to the first, and maybe the most important tool in the whole kit. It's based on a simple idea. If you can't count things one by one, you just start counting them in big groups.
And we do this all the time without even thinking about it, right? We buy eggs by the dozen. A dozen is just a handy word that means 12 things. Well, chemists needed their own version of a dozen, but for atoms, a word that stood for a specific and, frankly, enormous number of particles. And that word is the mole.
So here's the key takeaway. A mole isn't some super complex, scary concept. It's just a number. It's the chemist's dozen. It's just a convenient way to talk about a massive amount of tiny little particles, atoms, molecules, whatever, as if it were a single thing. But just how massive are we talking?
Yeah, that huge. 602 sextillion. It's a number so big, our brains can barely even process it. Which is exactly why no one ever writes it out like this. To put it in perspective, if you had 1 mole of marbles, they would cover the entire surface of the Earth in a layer about 50 miles deep. It's just staggering.
So this ridiculous number actually has a name. It's called the Avogadro constant. It's the magic number that lets us wrap up atoms into these nice, countable bundles we call moles. Okay, great. So problem 1 is solved. We can count atoms in groups. But how on earth do you weigh these groups?
This is where it gets really clever. This is the part where we build a bridge, taking us from that invisible, atomic world right into the real-world lab, where we have scales and can actually weigh things out in grams.
The solution they came up with was, frankly, genius. They just stopped worrying about an atom's actual, tiny, impossible-to-measure mass. Instead, they just decided to compare everything to a single standard, one specific type of carbon atom, carbon-12. So now, we can just say an oxygen atom is about 16 times heavier than 1/12 of that carbon atom. It's all relative. And this system gives us something we call relative atomic mass. The key word there is relative. It isn't an actual weight, it's a ratio, a comparison. And because it's just a comparison, you'll notice it has no units. It's just a number that tells you how heavy an atom is compared to our carbon standard.
Okay, now get ready, because this is the magical part. This is the trick that connects everything. That number, the relative atomic mass we just talked about, well, it turns out that it's the exact same number as the molar mass, which is simply the mass of 1 mole of that element measured in grams. So an oxygen atom has a relative mass of 16. That means 1 mole of oxygen atoms weighs exactly 16 grams. Boom! That's the bridge.
And from there, the logic just flows perfectly. Now we can figure out the mass of an entire molecule, like water, H2O. It's just simple addition. You've got 2 hydrogens with a mass of about 1 each, and 1 oxygen with a mass of 16. You just add them up. 2 times 1 plus 16 gives you 18. So the relative mass of a water molecule is 18, which means 1 mole of water weighs 18 grams. It's that straightforward.
All right, so we have our tools. We've got a way to count these tiny particles and a way to weigh them. Now, let's put these tools to work and see how we actually use them to understand and predict what's going to happen in a real chemical reaction.
Honestly, the best way to think about a balanced chemical equation is to just see it as a recipe. That's all it is. It tells you your ingredients, what chemists call the reactants, and it tells you what you're going to make, the products. And most importantly, it gives you the precise proportions. This whole idea of recipe reading has a fancy name. It's called stoichiometry.
Now this is where our new toolkit becomes a kind of superpower, because now we can look at this one recipe and read it in 3 different, incredibly useful ways. We can think at the tiniest possible scale,
2 molecules of hydrogen react with 1 molecule of oxygen. Or we can scale it up with our new counting unit. 2 moles of hydrogen react with 1 mole of oxygen. Or, and this is the really practical one, we can take it right into the lab and read it in grams. 4 grams of hydrogen react with 32 grams of oxygen. They all describe the exact same perfect ratio.
But, life is messy. In the real world, you almost never have the perfect amounts for your recipe. So what happens then? What happens when you run out of one ingredient before the other?
Well, this brings up a super important idea called the limiting reactant. It's just like baking a cake. The moment you run out of flour, you're done. You have to stop. In this first scenario here, we've got tons of hydrogen, but we use up all the chlorine. That makes chlorine our limiting reactant. It's a thing that stops the whole process cold.
But here's the thing. It's not like chlorine is always the limiting one. It completely depends on what you start with. So if we flip the starting amounts, like in this second experiment, now the hydrogen runs out first. It becomes the limiting reactant, and we're just left with a bunch of extra chlorine sitting around with nothing to react with. Understanding this is absolutely key to doing chemistry efficiently.
So let's just pause for a second. We've gone from a seemingly impossible problem, counting invisible atoms, all the way to predicting the outcome of real-world reactions. So let's zoom out and really appreciate just how powerful this simple set of tools actually is.
This right here is the so what. Why does all this matter? Well, because this toolkit is the foundation for pretty much all of modern chemistry. It's how we calculate the exact dose of medicine in that bottle. It's how scientists figure out the basic formula of a brand new material they just discovered. It's how chemical plants maximize their output, and it's even how we can measure the purity of something like gold.
So let's just recap the whole toolkit. It's really just a series of problems and their brilliant solutions. The problem? Counting invisible atoms. The tool? The mole. The problem? Weighing those atoms. The tool? Molar mass. The problem? Using them in reactions. The tool? Stoichiometry. Each one perfectly solves a fundamental challenge.
It's pretty amazing to think that this all starts from a simple idea, counting things in groups. But that one idea, once you build on it, becomes the very language of modern chemistry. It lets us describe and even engineer the world at its most fundamental level.
And really, that's the power we've unlocked here. The ability to precisely measure and manipulate the unseen world all around us. It gives us this incredible control over matter itself. So I guess that leaves us with one last big question. What are we going to choose to build with it?